Hi everyone, my name is Leela Manakrishna and I am from CSCC and my roll number is 5I0. Today I am going to present a seminar from the subject Applied Physics and I have taken the topic Domain Concept of Ferromagnetism. So I am going to explain this topic. So this is a seminar from the Applied Physics Domain Concept of Ferromagnetism. So domain concept of ferromagnetism. Firstly, we propose the concept of domains to explain the hysteresis effects observed in ferromagnetic materials as well as to explain the properties of ferromagnetic materials. So Weiss is a scientist who proposed the concept of domains to explain the hysteresis effects observed in ferromagnetic materials and to explain the properties of the ferromagnetic materials. The region in a ferromagnetic material where all the magnetic moments are aligned in the same direction is called a domain. So domain is a region in the ferromagnetic material where the magnetic moments are aligned in the same direction. A magnetic domain is completely magnetized and has definite boundaries. So it has a definite boundary. So a ferromagnetic material is divided up into these small regions called domains, each of which is completely magnetized. So in a particular region or a boundary, the domains are present and they are aligned in the same direction. Each of them are completely magnetized. Next, if we see the diagram, we can observe the boundaries, that is domain wall, and inside the boundary there are each chamber. It is called a domain. So a ferromagnetic material with domains, the dipoles are oriented in the same direction. We can see that in a specific domain, the dipoles are oriented in the same direction, which is completely magnetized. Next, the direction of magnetization varies from domain to domain. As we have seen from this figure, all the domains, all the direction of magnetic field is not in the same direction. They are having different, but in a particular domain, they are all aligned in the same direction. So the direction of magnetization varies from the domain to domain, and thus there is no net magnetization in the absence of external magnetic field. If there is no external magnetic field, there is no net magnetization. When the ferromagnetic material is placed in an external magnetic field, then there may be two independent processes. When a ferromagnetic material is placed in a particular external magnetic field, there may be two independent processes. And in the initial stage, when the external field intensity is low, so the external magnetic field is having low intensity, the size of the domains which are in the direction of field will grow. If the size of the domains which are in the direction of the applied magnetic field, they will grow. So from the figure, there are four cases. Variation of domains with external magnetic field. Now we are going to study the variation of domains in the presence of external magnetic field. So in the first figure, we are having four domains separated by a boundary, that is domain 1. And they are having different directions. And in the second figure, that is B, external magnetic field is applied in the upward direction. So one domain is in the direction of applied magnetic field and remaining are in the different directions. So if we apply specific external magnetic field to the domain which is in the same direction of the external magnetic field, it will increase and the remaining will decrease. And in the figure C, we can observe that if the intensity of the external magnetic field is increased much than in B, the other domains will also be aligned in the direction of the external magnetic field. And at the last, we can see that all the domains will be in the same direction. So the first case is no external field. If external field is not present, so there is no change in directions. And in the second one, growth of domains when the external field intensity is low. So there is a growth of domain which is in the direction of the external magnetic field. And the intensity is not sufficient for them to align in the same direction of external magnetic field. So just there is a growth in domains. And in the third case, a rotation of domains when the external field intensity is high. So from figure 2 and B and C, we can observe that rotation of domains takes place. So here In B, the top one is in the horizontal position, and in the C, it became vertical. So there is a rotation due to the external magnetic field intensity is high. So in figure C, you can observe that one. And in the last one, complete rotation of domains in external field direction, that is called saturation. So complete rotation of dimensions is observed, domains is observed in the external field direction only. So these are the variations of domains with the external field. Similarly, if we demagnetize the ferromagnetic material, so basically we are observing all these variations when we are magnetizing a ferromagnetic material. So we are having 4 cases when we magnetize. So if we demagnetize the ferromagnetic material in the initial or original domain, arrangement cannot be attained. So if we demagnetize, again, the previous one where external field is not applied, that pattern cannot be attained again. That arrangement of domains cannot be attained. This is mainly due to the disturbance in the formation of block walls, which we can read it as block walls also. So the original domain arrangement is not observed because the formation of block walls, which are present between two domains. Between domain to domain, we have already seen that is domain wall. So block walls will be formed between two domains in the reverse direction. That is, while decreasing the applied magnetic field. When we are decreasing the magnetic field, the block walls will be formed. This creates hysteresis in the ferromagnetic substances. Okay, now I'll explain briefly about it. First, domain concept of ferromagnetism. We propose the concept of domains to explain hysteresis and properties of ferromagnetic materials. The region in a ferromagnetic material where all the magnetic moments are aligned is called domain. Magnetic domains, ferromagnetic divided into small regions called domains, and each of which is completely magnetized. Next from the figure, domain wall and domain. Direction of magnetization varies from domain to domain in the absence of external magnetic field. When it is placed, there are two independent processes. In the initial stage, size of the domain which are in the direction of field will grow. And from the 4 cases we have studied, first one in the absence of external field, second one growth of domains when field intensity is low, third one rotation of domains when intensity of the field is high, complete rotation of domains. If we demagnetize, it will not able to get the original arrangement. This is due to the disturbance in the formation of block walls which are present between two domains in the reverse direction while decreasing the applied field. This creates hysteresis in the ferromagnetic substances. So now I would like to explain the last ferromagnetic domains briefly and hysteresis also. Ferromagnetic domains are small regions in ferromagnetic materials within which all the magnetic dipoles are aligned parallel to each other. I have already explained before, but now I am explaining it briefly. So ferromagnetic domains are small regions in a ferromagnetic material within which all the magnetic dipoles are aligned parallel to each other. So from the figure, we can see that the first one domains randomly aligned, and the second one in the presence of external field, the domains are aligned in a proper way. So in the first one, we can see all the domains are irregular or within the domain, they are parallel only. But when comparing to all the domains, they are not parallel, they are arranged in the random manner. So in the second figure, we can observe in the presence of external field, they are aligned in a unique manner. Next, we have the term hysteresis. Hysteresis is the common property of ferromagnetic substances. It is a property of a ferromagnetic material. Generally, when the magnetization of ferromagnetic materials lags behind the magnetic field, this effect can be described as the hysteresis effect. So what is hysteresis means? When the magnetization of ferromagnetic material lags behind the magnetic field, this effect can be described as the hysteresis effect. Thank you. So now I have briefly explained about domain concept of ferromagnetism, and I have explained also the domain concept, domain ferromagnetic domains and also the hysteresis. Thank you. Hope this helps you.